So good morning, everybody. So my name is Sebastien Boulnois. I'm a French Ph.D. student at the School of Human Centered Design, Innovation and Art at Florida Tech. I'm doing research on onboard weather system, and more specifically on the one that we are currently designing at the school, which is the onboard weather situation awareness system. Today, I'm going to focus on the approach that I used in order to develop this prototype. So first, let me begin with two facts. Between 2000 and 2015, FA reports say that weather has been involved in 68% of the delays in the US national airspace system. On the other hand, NTSB reports say that weather has been involved in 34% of US commercial aviation accidents. So let me go a bit deeply in these facts. So first, regarding the delays. First, the air traffic is saturated. And these numbers provided by Airbus show us that it's not going to get better in the next 20 years. In addition, here's a scheme showing the number of delays since 15 years in the US national airspace system. So this is a huge amount of delays. So weather reduces the nominal air traffic capacity. So I think we should focus our work on longer-term weather planning methods. On the other hand, regarding the accidents, by reading some reports from NTSB, I found out that a poor weather situational awareness is a real issue here. So I tried to find a rationale at these numbers by orienting my research first of current onboard weather systems that pilots are using. So here are the current onboard weather radars. You have some of them. So I classified them with three categories: the content, the visualization, and the interaction. So first, most of them provide pilots with the reflectivity of the precipitation, which is close to real time. However, there is a big point here. This is attenuation. So when pilots are facing a big weather system, when they are flying, they might not be able to see what's behind. In addition, frozen reflectivity is really hard to detect. And the accuracy is fine, but only up to 80 nautical miles, according to pilots' input. Regarding the visualization, so some of them have a bird's eye view, so it's an orthogonal view. So this is good for precise navigation and measuring the distance, but it could be hard to interpret 3D information because it's only a 2D view. Some of them have two views, a bird's eye view and a profile view. So here, it's a lot easier to interpret 3D information, but it might require some mental integration from the pilots. Regarding the interaction, these systems have mainly two modes, the range mode and the manual tilt mode. So both of them are fast and easy to use with user experience. So pilots have to be skilled for that. On the other side, the first one is line of sight limited and the second one is degrees limited. I also looked at some onboard weather systems that have been developed or that are being developed to help pilots to deal with weather. So at the top you have navigation displays, and at the bottom you have more mobile weather applications. So I analyzed these tools too with the same pattern than the weather radars, and I mainly found that some work should be done on the interactivity part and the mental integration as well. So by taking into account all these advantages and drawbacks, we tried to combine everything and to have a system that could help pilots. So we designed this system. Of course, this couldn't have been done without collaborative work. So I have a team for that matter. So we were psychologists, programmers, professional pilots, and some teachers too. So here's an overview, but I'm going to come back on it later. So in order to develop this system, we used what we call the human-centered design approach, which is strongly emphasizing the human systems integration. So I'm going to talk about that a little bit. So first, why do we design a system? So this answer generally comes from statements and from requirements generated from the potential users and or any other entity involved with the system. Then you have the design decisions. These are the solutions that are that can be developed for the system. Then come the prototype development, and then two main parts here: the integration of the system in the existing environment. So here we're talking about integrate the system with the pilots in the cockpit, and the human-in-the-loop simulation. So evaluate the system in the environment. So now we have all the tools, all the modeling and simulation tools that are enough powerful, so we can integrate the pilot, the system, into the cockpit, and we can observe the pilot's activity. And we can discover emerging properties that cannot be discovered at the design time, only with the designer. And then after, this gives us testing results that we can use for the next iteration design. So I'm going to go deeper in each step now. I'm going to show you how this happened. So first, as the main goal was to deal with weather situation awareness, we first conducted interviews with professional pilots in order to generate useful requirements. So we asked them relevant questions about weather aviation, which kind of weather information sources they have access to, these things like that. And all of them agreed on needing solid and liquid precipitation information, and everything about turbulences and wind shears information. So here, this was collaborative work with professional pilots. Then we decided to work on this precipitation solution. So we needed a representation for this precipitation. So we designed 4 solutions here in order to validate at least one of them. So here again, we performed interviews again with professional pilots so they could give their feedback. So we asked them what was the best solution according to them and why, because this is the most important part. So they chose these two ones, the point cloud and the polygons. The first one because it reflects the reality. This is coming from NOAA servers, and this is pretty accurate. And the second one because it was quite consistent with what they have currently in their visuals. And thanks to all this information, we were able to develop this prototype. So here again, collaborative work was in the place for that. So I'm going to describe the system quickly. At the top part, you have a globe. At the bottom part, you have a map. You have flight waypoints. You have flight path in magenta. You have weather information available all along the flight path. You have, regarding the visualization, you have 2 views. You have a bird's eye view that is at the bottom, which is a world reference view. You can see the global flight. And at the top, you have an exocentric view. These 2 views are synchronized with each other. So when you see an area of interest in the bird's eye view, you can just click this area, and the 3D is going to be synchronized, and it's going to bring you to this area, and you're going to be able to more specifically study this area in 3D. Regarding the interaction part, you can do pretty much everything. You can pan left, right, up, down. You can rotate. You can zoom in, zoom out. You have tilt features. So this covers pretty much everything. So the next step consisted in integrating the system in the existing environment with the pilots, so we could observe their activity as they were performing a real flight. For that matter, we have 2 aircraft simulators at the school that are a Boeing 737 and an Airbus 320. However, this step required our system to be fully synchronized with the simulator. And this took a bit more time than we expected. So consequently, we first tested the system by itself. So we chose to perform formative evaluations with professional pilots by using subjective methods. Why? Because at this step of the design, we just wanted to generate trends, so we could focus on work on specific things for the next design iteration. So, of course, we also generated, we assessed some criteria such as situation awareness, cognitive compatibility, usability, and some workload. But here again, we didn't look for generate any statistics. We looked for trends, so we could generate design priorities in order to know what to work on for the next design iteration. So that's it. Human-centered design approach is an iterative process. The more you're going to go through these steps, the more your system will be refined. So here are some discussion. So far, for this step of design, I only took into account the pilots, the system itself, and the tasks that are associated with everything. But there is an important point that I didn't take into account so far. This is the organizational part. So during the interviews with the pilots, they told me that air traffic controllers, dispatchers, and airliners, for example, have a crucial role when dealing with weather and flight trajectory modification. Another thing is that we also have to refine our synchronization between our system and our simulators, so we can fully integrate the system in the environment, and we can observe the activity. So as a conclusion, here, whether situation awareness is addressed, our system tries also to complement the tactical approach from the weather radars by bringing this strategical approach with the weather all along the flight path. Collaborative work, participatory design was the key here, because at each step of the work, we were able to, we worked with all the people, the professional pilots, and this was really useful for having a pretty good system. Human-in-the-loop simulation is really important here. So this design is a work in progress, so it's pretty new. We began to work on it in May. So this is based on previous versions of the system that has been developed some years ago. And for the next work, of course, I want to take into account everything I said in the discussion part, but I would also like to focus my work on the visualization aspect. So which kind of views, which kind of combination of views should I use in order to improve the weather situation awareness of the pilots? So that's it. Thank you.
Thank you. Thank you for your very interesting presentations.
You're welcome.
I had already some snapshots of it when I visited you.
Yes.
With regard to these loops that you mentioned,
Yes.
that go to more and more refinements in your own work.
Yes.
This is a question also relative to systems engineering. What about the convergence? What about stability issues? Where in fact when you go through more and more loops, you get to a solution, you converge to it, or possibly you never converge. You might diverge occasionally. It's a real systems engineering issue.
That's right. So I think that during these steps, flexibility is the key. So the more you make progress on the development of the system, the more you have to be careful about what you wanna fix and what you wanna leave flexible. So if we have some divergences, we can still maybe catch up thanks to the flexibility that we left in the design phase.
Good morning.
Good morning.
Yes. Just a comment, actually, and maybe just useful.
Yes,
point of
of
reference
course.
in your work. So
Yeah.
a lot of the, I mean, I don't know the pool of pilots that you interviewed. In the beginning of the presentation, you made obviously clear reference to tilt-based radars, and as you probably know, manufacturers like Honeywell, we're moving away from tilt-based radars for some of the reasons that you mentioned, because pilots generally have very, very difficult, they have great difficulty in correctly managing tilt and gain and these sorts of things. So in terms of trying to understand some of the issues, I suppose what I'm really trying to say is if your pilot population is that you interviewed was based exclusively on those that have experienced with tilt-based radars, I mean, there's going to be a natural bias, and so the way forward, and really the way forward, of course, is, as I mentioned, we've moved away from tilt-based radars. So it's just a minor, well, it's not a minor point, but it's a specific point, because trying to elicit requirements based on old information based on old radars is going to skew your data.
Okay,
and then the other point was, you talked about radar attenuation being a problem. So in your work, I mean, how are you addressing that?
So far, I'm using the information coming from the ground radars. So I'm using the NextRad network, and so that's how I can display the weather all along the flight path. So that's how I deal with the attenuation so far. You're welcome. I have a question there.
Catherine?
Just because it's a session about tangibility, and I have understood from Gilroy presentation yesterday that you are interested in tangible objects, and it's apparently it's a touchscreen application. So are you going to evolve it in a tangible system?
So far, we used to choose a tablet for flexibility reason, again, because it's easily, we can integrate it easily in the cockpit, we can move it everywhere. We don't know yet how is it going to be implemented at the end, if it works, if it's good. So that's why we choose the tablet-based thing so far. But this could be improved in other maybe platforms, but so far, we don't know yet.
Thank you, Sebastien.
Thank you.